All right, continuing our discussion on electrochemistry. One of the things that we do with our electrochemistry that we just saw with batteries is we move electrons through wires in order to do work. And if we want to move something that has a mass, then we have to do some work. And the way of thinking about electrons moving through a wire is the same way that water moves through a hose. It moves from an area of high pressure to an area of low pressure. And you can kind of think of the same thing as far as potential energy for electrons moving from one material to another. So that's what causes this pressure in an electrical circuit. There's a potential energy difference in the materials used for the electrodes, and they always want to go to something that is more stable, so the electrons will move from something that's not as stable to something that is more stable. And we measure this potential energy in the unit of volts, and what's actually moving them is called the electromotive force, that EMF. So we measure that force in volts. Now, the volt is actually a derived unit. It is a standard unit, but it's also a derived unit. It's the amount of energy needed to impart 1 joule of energy to an electric charge of 1 coulomb. And we'll see where that becomes important a little bit later in one of the other parts. And the amount of charge contained in 1 mole of electrons is right around 96,500 coulombs, which is an enormous amount of charge. But we call that specific amount of charge a Faraday. And again, this unit will be used a little more in a coming part. So more on EMF. There's a lot of factors that affect the voltage that comes from a cell. And so in order to standardize what we would expect a voltage to be between two materials, we have to have a set of conditions under which we measure those potentials. So we have a standard set of conditions, and from those we measure standard potentials. And those conditions are the reactants and the products have to be in their standard states. Any aqueous solutions have to be at 1 molar. Any gaseous substances have a pressure of 1 atmosphere. And the temperature has to be 298 Kelvin. Now again, these are your standard conditions. We can certainly have measurements done under non-standard conditions, and we'll talk about those later as well. Okay, now when we measure a cell potential under those standard conditions, we have something that is called E0 cell. So E cell, I always used to think of the electricity from the cell, so that's the voltage from the cell. And that little 0 there, just like we had for all of our thermodynamic measurements, that little 0 means that it's measured under standard conditions. So we just use the term E0 cell. So how do we find that E0 cell for an electrode? Well, each electrode has its own potential as measured against a standard hydrogen electrode. Remember, we mentioned that the standard hydrogen electrode is like sea level. So just like here on Earth, we have some places that are higher than sea level, and so they would have a positive elevation. And then we have other areas on Earth that are below sea level, and if we put them on a number line, they would have a negative elevation, as opposed to just saying below sea level. We set that standard hydrogen electrode right at 0 volts, and because we have to worry about, are we looking at reduction process or the reduction process, oxidation process or the reduction process, we want to make sure that's standard as well. And so all of our potentials are tabulated as reduction potentials. Even if something doesn't want to be reduced, we still show its reduction reaction and give it a reduction potential. So we have 2 different ways of measuring E0 cell. The first one seems a little bit more straightforward, but it involves an extra step. I show it just so that you can see it. Some people learned it this way, where you have E0 cell is equal to your oxidation potential plus your reduction potential. Now, we mentioned that the values in the table are reduction potentials only. So what you would have to do for a half reaction's oxidation potential is you would have to just change the sign of the appropriate half reaction and then add the two potentials together. So add the changed sign value from the oxidation potential to the tabulated reduction potential, and that will give you E0 cell. Okay, so yeah, I just mentioned that. Now, the method that I tend to use more often is this one here, where we have E0 cell is equal to E0 cathode minus E0 anode. And so here we use just reduction potentials listed in the table. And based on where the materials lie on the table of reduction potentials, you can figure out which half reaction is going to be the cathode, which of those is going to be the anode. And here we can just subtract the two reduction potentials in this way. So E cathode minus E anode, and it will give you E cell. Neither method is better than the other. They will always give you the exact same value if you do them properly. So it's kind of like the oil rig and Leo goes grr. Pick one of those methods and always use that method. They will both always work. There's no situation where one equation works and one does not. They're exactly the same. They're just manipulated a little bit. Okay, now another thing that's very important when you're measuring E0 cell is that E0 cell is an intensive property of a cell. And that means that the amount of material in the electrodes does not affect the voltage. It also means that if we have to multiply a half reaction by a value to get the right number of electrons, we do not change the voltage for that half cell. So that's a mistake that is very commonly made. Another way of thinking about that is if you think of all the common batteries, the AA's, AAA's, D's, C's, they're all different sizes. They have different amounts of material in them, but they all have the exact same voltage. And that's because they have the exact same chemical cell in them. So the amount of material does not affect the voltage of that cell. The only thing that affects it is what reaction is taking place. So let's go back and look at our copper-zinc reaction as an example. And so there's our copper 2 plus zinc goes to zinc 2 plus copper. We'll assume that we have a standard cell here, so all aqueous solutions are at 1 molar. So this is an example of what a reduction potential table might look like. This is a very abbreviated one. It doesn't include all the half reactions by any stretch of the imagination. So this just came out of a textbook. But here we see that we have copper and zinc involved, copper 2 plus going to copper and zinc going to zinc 2 plus. So we just need to look up our zinc half reaction and our copper half reaction. And so for copper half reaction, we see that right there at 0.337. And for our zinc half reaction, we see it at negative 0.763. Now notice in our reaction up here, the zinc is actually an oxidation reaction, but down here it's a reduction reaction. Remember, all reactions in this table will always be written in a reduction half reaction. What you need to look for is, does it have the appropriate species? We're dealing with zinc and zinc 2 plus, and here we're dealing with zinc and zinc 2 plus, and so that is the proper half reaction. You do have to be careful about some things. So like, for example, this copper 2 plus 2 electrons going to copper. I know in a more extensive table, you'll see copper 1 plus an electron going to copper metal. You will also see copper 2 plus an electron going to copper 1 plus, and that will have a different reduction potential. So you always want to make sure that you look up the appropriate reaction. Okay, so we have copper is the reduction reaction, so that will be the cathode. So we're going to have E cathode minus E anode. And so since we're going to use E anode, we use the reduction potential of the anode. And so we have the 0.34 for the copper minus the negative 0.76 of the zinc. And so really all we're doing is saying, what is the difference between these two values? So it's just like working on a number line. And so the difference in value between 0.337 and 0.763, negative 0.763, is 1.10 volts. So if I have a 1 molar solution of copper, a 1 molar solution of zinc, and I put in copper metal and zinc metal, and I hook a wire up between those electrodes and I measure the voltage there, I can expect to see 1.1 volts come out of that cell. Okay, so now that we have a table of reduction potentials, and your book has a very extensive one in the appendix in the back, we should be able to look at any material that we're dealing with and figure out a lot of things about a battery made between two different materials. So if we were to make a standard battery out of aluminum and nickel and the appropriate aluminum solutions and nickel solutions, what we should be able to find at this point is the cathode, the anode, the oxidizing agent, the reducing agent, the overall reaction, the direction of electron flow, the number of electrons transferred, and the cell voltage. The number of electrons transferred is just the number of electrons that you have to get when balancing the reaction. So how many electrons did you need to get for that lowest common multiple?